We're back now with my Kabarak paper 1. Thank you for joining. Welcome. This is the paper. It's always very important that we can get to touch. Then now we can go through the paper. Thank you. The diagram below shows the Earth moving around the Sun continually. See the branch of physics that would be concerned with this. The Earth is in motion. Therefore, the part of physics that is involved with motion, it is the mechanics. The mechanics is well involved with the diameter of steel using a Vernier caliper, which has 10 divisions of 0.1 centimeters on the main scale, 10 divisions of its Vernier scale, and then we have 9 division on the main scale. In this case, the first thing we are supposed to calculate what is the least count. Therefore, from the main scale, we are having 0.1 centimeters. Then from the Vernier scale, where we are told we are having 9 divisions, and it is matched by 10. Therefore, it will be 9 divided by 10, arrive at 0. Let it be 9. Yes, 0.9. Then now this one, you will pick it and multiply it by this 0.1. You arrive at 0.09. Then you'll pick 0.1 to get the least count. It will be 0.1 minus 0.09. And we're going to arrive at 0.01 centimeter as our least count. Therefore, we're having all this, and then we are told that it has a negative error. Calculate the mean corrected, then mean corrected diameter of the steel ball. In this case, may I repeat, if the zero error is negative 0.03 centimeters, calculate then the mean corrected diameter of the steel bar. We first get the measurements, the first 3 measurements. So the first one will be 0.5 plus 8 times 0.01. And in this case, you'll arrive at 0.58. The second one, it will be 0.5 plus 4 times 0.01. then you're going to get 0.54. The third trial will be 0.5 plus 6 times 0.01, and this is 0.56. Then in this case, you're going now to get the average. The moment you are getting the average, then the principle of averaging must be shown. Therefore, 0.58 plus 0.54 plus 0.56, then you divide by 3, you get 0.56 centimeters. Calculate the mean corrected diameter. So in this case, we will avoid the error because we're looking for the mean that we got as a reading from the Vernier scale. The next question. We are told that a wooden block on a horizontal surface is pulled by a constant horizontal force T, as shown in the diagram. At two different sections, the block moves with constant velocities along xy. Section xyp is rough, while pq is smooth. Use the information to answer questions that follow. Then you can see where x is, where our y is, where our p is, and where our q is. Then we're told describe the motion of the block as it enters section PQ. Then it is moving from a smooth surface, from a rough surface to a smooth surface. Therefore, in this case, we expect the velocity of the body to increase. At long last, this one will say the body accelerates. It accelerates. Give a reason for your answer. It is because now we are moving from a rough decrease in frictional force. Kinetical will lag as equal volumes of water as TA and TB, as shown in the figure. Water in A is at 45 degrees. B is at room temperature 25 degrees. Then you are told cold water is poured carefully in A, and simultaneously an equal mass of hot water is poured in B. Then now you are told state which of the thermometers record a lower reading after a short while. a mass of hot water is poured at B. We expect this one to be more dense, less dense. Therefore, we have added cold water, and now we are adding hot water, sorry. That is what is being added there. Therefore, start with which of the thermometers record a lower reading after short while. In this case, it will be TB. Why? Why does it record a less temperature? Then, cold water in air mixes faster by creating convectional currents. Unlike in B, which will be denser than cold water, which can be like in B. You can change this one. Then you go for TA. Now we keep explaining. Unlike in B, which will be denser, which will be less dense, which will be less dense. A stone of 200 grams is whirled in a vertical circle at a constant when the stone is at the upper pass. Therefore, At lower part, we say that T is equals to mv squared over r plus mg. And in the upper part, we say T is given by mv squared over r minus mg. Therefore, we go for T is given by mv squared over r minus mg. Therefore, T is given by, the mass is 200 grams, which is equivalent to, can say 200 divided by 1000 times V, which is 3 meters per second. 3 meters per second. Then we square it. Then divide by the radius, which is 0.4 minus 200 or 1000 times 10 G. And this one leads us to 4.5 minus, then this one leads us that T will be the same as 2.5 newtons. T will be the same as 2.5 newtons. Below is a solid frustum of a cone resting on its narrow end on a horizontal flat surface. The solid is made of a uniform metal. The name, the state of equilibrium of the solid. If you look at it, but before we answer that part, let's try to identify the center of gravity. Then this is the way. So this is the COG. If you look at the positioning of the COG, the moment you slightly tilt this frustum, it will still come back to its normal position, meaning that it is in a stable equilibrium. It is in a stable equilibrium. Locate this and you mark it M. So now I have to delete my COG and put my M as per the instruction of the question. Some pollen grains were placed in water to study Brownian motion in liquids. State and explain the nature of the observed motion. We do expect to see these pollen grains moving in a constant random motion. And now we need to explain what do you see and why is it happening. So the pollen grains are observed to be in a constant random motion. And why is it? This is because they are being eaten by invisible liquid particles. By invisible liquid particles. Can proceed to the next part. When estimating the diameter of an oil molecule, a student measured the diameter of an oil drop using Vernier calipers. Set one assumption of this. Remember now we are talking of the oil drop. So in this case, it must have been spherical. spherical. It is spherical. And now, a Form 1 student at upper secondary school had a tin can half filled with water, as shown in the figure. Then we were told she heated and the water let it to boil for some time. Then the open top, this one, was then sealed and cold water was poured on the can. The can was observed to crash. So in this case, after you lock it, we expect the can to crash in this manner. And this one is brought about by issue of trying to balance atmospheric pressure and the pressure inside the can. Therefore, why was water let to boil? One was to expel the air, to expel out the cold water poured on the can. Or you'll be having a boiling, then it will produce some steam. It's going to produce some steam. Therefore, if you suddenly pour some cold water, then during the condensation period, you're going to create a partial vacuum. Therefore, the purpose of this one is to condense the steam. And explain now why this one. So upon heating, you created some steam. This steam was suddenly cold. Then after cooling, now you created a partial vacuum. So on sudden cooling, a partial vacuum is created. This one means low pressure zone. So higher atmospheric pressure crushed the can inward. So now we are talking of this is RTM. Now we may proceed. You thought that the temperature of a gas in a container of fixed volume was gradually lowered and the corresponding pressure measured. Below is a sketch showing the variation of pressure with temperature from the experiment. You can see this is the pressure, this is the temperature. Now we may proceed to the question. Define the pressure at X using kinetic theory of matter. Pressure at X using the kinetic theory of matter. Temperature at X, this is it, is the absolute zero temperature. And this one, you can say temperature at which the kinetic energy is 0, then what do we do? Particles are assumed to be 0. See the reason why temperature X cannot be achieved. Remember, this one is just for an ideal gas, not just. Then the gas will be highly squeezed. But if you look at the pressure there, the pressure will be very low. Then it is for an ideal gas. It is for an ideal gas only. A steel wire of length 20 centimeters was coiled several times to make a spring. The spring was loaded with various weights. The graph of force against extension plotted. This is now in the Hooke's law. Then state two changes that could be made on the spring to obtain the graph in figure 2. In the first one, we can see somehow they are somehow proportional. So we are using, I can say they are almost proportional. But when it comes to Roman 2, we can see that we are using very little force to create a large extension. Less force, more extension. This means that this will be a spring. State any two changes that will be made on the spring to obtain. Then this case is when in case we increase the number of turns per unit length. And number 2 is in case increasing the diameter of the spring. Case of increasing the diameter of the spring. And this tells us how these two factors affect the spring constant. State the principle, apply this principle. For a fluid, which is incompressible, as streamline flow, and is non-viscous, then we say an increase in velocity leads to a corresponding decrease in pressure. In deriving the equation of continuity, explain the effects of increase So that explain the effect of increase in fluid viscosity on the type of flow. So this one you can say the more viscous, okay, an increase in viscosity. This can be brought about by issues to do with increase in density. Then may lead to turbulent flow. The figure below shows an increase, shows water in a horizontal tube of two different sections, AB, AB, and BC. Then we're told the cross-sectional area of the piston is 1.5 square centimeters, while that of section BC is 2.0 millimeters. If the piston moves 12 centimeters from A to B in 3 seconds, calculate the volume flask. Then in this case, volume flask is given by the volume over time. Therefore, we are having a cross-sectional area of 1.5 and 12 centimeters. I think in this case we can work with the small units. Therefore, 1.5 1.5 times 12, you divide by time of 3 seconds. In this case, you'll arrive at 6 cubic centimeters per second. 6 cubic centimeters per second. Then now you are asked about the speed of water through section B. In section B, before we move to that, we must calculate the velocity in A. Then for us to get the velocity in A, V1 will be given by the volume flux, by the distance over T, which will be 12 centimeters divided by 3. And this will be the same as 4 centimeters per second. Then now we can continue. Yes, now you can continue. Now we must look at the speed of water through P. Then from equation of continuity, area 1 V1 is equal to our area 1. This will be given by 1.5 before you change the 1.5 centimeters squared, convert it into SI units. Then now you multiply by velocity 1, which we have got as 4 centimeters per second. As 4 centimeters per second. This is equivalent to 0.04 meters per second. This is equals to area 2, which is 2.0 millimeters. This one is same as 2.0 times 10 raised to power negative 6, convert into square meters. Then now we are in search of velocity 2. Then V2 will be the same as 1.5 times 10 raised to power negative 4 times 0.04 divided by 2.0 times 10 raised to power negative 6. Our V2 will be the same as, finally, 3 meters per second. And if you look at that one, we can see an increase from 0.04 meters per second all the way to 3 meters per second, proving that we are very much correct. Below is a figure that shows cross-sectional diagram of a carburetor used to supply petrol for combustion in a car engine. This is how it is. You're told, explain how this carburetor is able to draw petrol into the combustion cylinders. Explain how the carburetor is able to, therefore, air is sucked in the venturi these parts due to action of engine piston. Then you are told fast moving air decrease the pressure at that part. Decrease the pressure. Then higher atmospheric pressure. High atmospheric pressure pushes the petrol up. Remember, this is an application of Bernoulli's principle. COVID vaccine, is only suitable when stored at a temperature of negative 40 degrees Celsius. A nurse had a choice of measuring the temperature of this vaccine using either a mercury thermometer or an alcohol thermometer. Explain which of the two thermometers will be suitable. Of course, she went for alcohol thermometer. alcohol thermometer, and it is because it can measure very low temperature. And you're also supposed to be more specific. Remember, this one can measure up to negative 115 degrees Celsius, whereas mercury is only up to negative 39. Below is a glass filled with a tube and inverted in water. Then you're told the temperature of the surrounding is slowly lowered. So this means that a decrease in temperature. A decrease in temperature. Then we're told states the observation on the liquid level in the glass tube. So the moment you decrease the pressure, the temperature, then you're going to alter some of the things. First thing is that we expect the glass flask first absorb, to first emit, to first emit and by emitting it to the environment, then it means that it is contracting. So after it contracts, it becomes very small. And if there is some little water inside the tube, they'll first lower in the tube. Then after some time, the coldness will come into the air. Then now air contracts. This will force the water to rise. Therefore, you say the level of water, the water level in the glass tube will first drop, then rise. Why? The glass will contract, reducing in volume. Later, air contracts. So once this contracts, it will force the water to drop. And then once the air inside contracts, now it means that it is creating some space for water to rise up. Give a reason for this observation. I think that is here. That is what you're supposed to. A glass bulb onto a hollow stem in a can. And a grid of equal squares. Use these separators to describe how to make a graduated whose scale is in Celsius. Therefore, heat the ice and allow it to start melting. Such the bulb into melting ice. And as y. Suspend the thermometer. Bulb in the space above water. Boiling. And the normal. And the normal atmospheric pressure. And mark the mercury level as Z. Now use the grids to divide YZ into 100 equal parts. Now you can continue the next part. That is a narration on the issues to do with graduating or making your own thermometer. The ratio as used in machines, you can say, is the ratio of effort distance to load distance. The figure shows a load of mass 220 kg pulled up an inclined plane with a constant force of 150 newtons. The plane makes an angle of 32 degrees with a horizontal and a height of 3 meters. Then now you're told, determine the work done on the load. The work done on the load is like lifting it from the base all the way to a height of 4 meters. Sorry, to a height of 3 meters. Therefore, in this case, we'll say lifting is like creating potential energy. Therefore, the work done here will be mgh, which will be mass of 20 times 10 times height of 3 meters. And these will be equivalent to 600 joules. Told work done by the effort. This will be work is given by the applied force times the distance it moved. But now here all the way. So in that manner, that will be our distance d. But how do we arrive at our distance d? This one we can use SOHCAHTOA, but our sign will be, our SOH will be 3 divided by sine of 32. Calculation, this will lead us to 5.661 meters as our d. Then now we can substitute now this. The force that has been applied is 150. A force of 150 times a distance of 5.661. And this one is going to lead us to 849.15 joules. The efficiency of the system. Efficiency is given by the work output over the work input times 100. But because of the spacing, we're going to use only 1. Therefore,